standard drilling, but it becomes very difficult once you're down at significant depth in the coral. So that core is about 6.5 meters long. Here are the 3 cores, and then for calibration with that buoy. So we develop an age model. I mean, corals, as many of you guys know here, they often produce annual growth bands, alternating dense and not so dense portions of the skeleton. The scale's about 1 centimeter per year here. And here's a sampling transect. So we count these bands, but we also do isotopic analyses. This is delta O18, and there's always a full cycle, that would be warm temperatures, down here is cold temperatures. So we kind of have a sense as to when the skeleton forms. You can't really produce a monthly scale chronology, but certainly quarterly, right? And then with 3 cores, we do the same kind of thing on all 3. We know what our standard error is for replication, like, how warm was it, how cold was it in 1492, for example. So there it is, the age model. This just shows the bands, but it's going back to, this is about 1470, and there's still about 4 meters of core left that we haven't been able to get out, but I think at some point, once we've published, we'll get funded to go back and get the bottom of the core. Okay, so what did we learn? This is the main take-home point. This is kind of a reflection of about 14,000 stable isotope analyses from different cores. So I split it up with Brad Lindsley, who's at Lamont right now, and Neil Tangri is my PhD student writing this stuff up for his dissertation. So it's delta O18, and if it's kind of the classic relationship to temperature, that's the range. And we do think this is mostly temperature because of our correlation between the upper 10 years of O18 with temperature data from that nearby NOAA buoy. It rains a lot there. We've collected the rain. It's first cycle rainfall, so it's about 0 parts per mil, just like the ocean, right? So you can rain all at once, but it doesn't change the O18 of the ocean very much. And so we do interpret this in terms of temperature. If you look at how the overlap with the instrumental record, it actually looks pretty close to the instrumental record with a low temperature in the early 1900s, jumps up, it flattens out again, jumps up. But there's much larger variability, right? So maybe this is the anthropogenic time, and it's definitely, we're at O18 values up here that indicate warmer water than at any other time in the previous, 450, 500 years. But there's some pretty interesting jumps here, and we worked a lot on this one, and we've analyzed it in all 3 cores, and it's always there. So we think that's a real jump and some kind of step function in the climate system. It's old enough, it's before the 1800s, that there aren't that many other time series that we can examine to compare this to, so we're still trying to sort that one out. But we have a pretty good sense of the natural variability and the magnitudes from work like that. There's a very strong ENSO signal here. I'm not going to show you the statistical analyses on that, but ENSO is strong and then weak and then strong over kind of a 100-year time scale. Let me show you one more example, this one from the Western Indian Ocean. It's work that we've done in Kenya, in Malindi. We even have a few coral cores from Somalia, and that was an interesting field experiment. But I'll show you our longest record comes from Malindi, which is right here along the Kenyan coastline, adjacent to one of the largest rivers here. And we've done some work on land use change. It turns out these, when the British came in they had this idea that they're going to turn Kenya into this highly productive system. They're going to grow coffee everywhere. So they did a lot of clear cutting in the Kenyan lowlands and planted coffee, which failed. And then they were left with this denuded landscape, which started dumping its soil into the rivers. And you can pick that up in the corals. The corals record the amount of sediments coming in Kenya's coastal rivers. And wherever we've sampled them, there's this big increase in sediment input in the 1910s and 20s. But today I'm going to talk mainly about a temperature record. And it kind of comes from work that Dirk Verschuren published on in Nature, Rainfall and Drought in Equatorial East Africa during the last 1,100 years. And he worked at Lake Naivasha. Has anybody been to Lake Naivasha in Kenya? Flamingo Lake, you've been there. It's where they make this really horrible wine. But if you have Kenyan wine, red wine, it came from Lake Naivasha. Lake Naivasha is an evaporitic lake, and through a series of sediment cores and some geochemical magic, he's estimating the depth of the lake here. And so the lake's gone up and down by about 35 meters as you go back through time. And there's some periods where they don't even, the lake was maybe overflowing, but it was certainly at a maximum level, separated by periods where the lake was either dry or very shallow. And that's a water balance thing. So these would be major droughts. And in the oral history of East Africa, they talk about these droughts, right? And the Lepernorat drought's the most recent one. And in between these mega droughts are these ages of prosperity. Lots of water, things grow, your cattle are fine, you're in an age of prosperity. And then the drought kicks in and society completely reassembles, right? So we were interested in mega droughts because, colonial history starts here and we haven't had a mega drought, right? But there's 20 times as many people. So what could a mega drought happen? And so we were actually challenged to address this question by Stefan Hastenrath, who had been working on Mount Kenya and Mount Kilimanjaro on records of precipitation of snowfall. So we used corals there. I mean, again, beautiful banding. You can see, these things record runoff from the rivers as well. But if you go back and do the isotopes, so here's delta 18 again from a long core. There's 1 degree centigrade using calibration. This is all monthly data. And again, a couple of things you can see. The highest isotopically inferred temperatures are in the last decade of the record, right? And they far exceed anything else in the preceding 300 years. Lots of natural decadal variability. It also looks kind of like the global temperature instrumental time series. But then you get way back before we have instrumental record. And here is the exact timing of the last mega drought, right? Lasted 70 years. 70 years. And Lake Naivasha just about dried up. And so the anomaly here would be indicative of water temperatures that are cooler by 2 to 3 degrees centigrade. How do you do that on the equator? We're within 1 degree of the equator. And what this would suggest is water temperatures are dropping down, 27, maybe 6 degrees centigrade below this kind of convective thermal limit, right? And the ocean's just too cold to generate enough vertical motion of moisture that can fall out on the land as rainfall. And so, that seems to be the proximal cause, but what could cause that kind of cooling? And that's a job for modeling. And modeling, we've engaged in some modeling there. Nobody's been able to produce that kind of a chilling effect. It does seem to be associated with cooling. East African waters are warming now, so it may be that we're moving away from conditions that allow mega droughts to happen in East Africa. But that question of climatic perturbations that result in very significant changes in rainfall in places where people are living close to the edge, that's something we need to be addressing. Okay, and this is the last coral slide. I pulled together all the published records of temperature change since the year 1900. This is all from corals, right? They're all in the ocean. We do have some instrumental data at some of these sites, but very few sites provide instrumental data that goes back, more than 40 or 50 years. So the corals, they're not perfect temperature recorders. In some cases, they're near instrumental quality. In most places, they're kind of just okay. So you beat down the uncertainty with replication and with multiple sites. But the quality, the fidelity of corals as thermometers, it doesn't change through time. I mean, you can go back 500 years or go to some fossil corals and go back 10,000 years. The basic physics of how those signals are incorporated in the carbonate crystal lattice are the same. So a couple of things here. The number is the site, and it's keyed to my caption. We're not going to look at it. But in the parentheses are the inferred temperature changes since 1900. And there's a couple of things I would say. there is somewhat evidence of equatorial enhancement of temperature change in the last century in the ocean. It's a little bit different from polar amplification. This would be an equatorial thermal amplification. There's some sense of warming being a little bit greater within this area of the warm pool. Not always. I mean, here's a minus 0.7, minus 0.2, but there's some, some big numbers up here as well. On average, so I mean, this kind of feeds into the notion that we will see a strong hydrologic response to global warming over the next century because of increased warming in the warm pool in places where heat is released to the atmosphere, sensible heat, it is latent heat, that the tropical hydrological cycles should ramp up, right? This would suggest that is the kind of world that we're heading into. And it's an insight that you can't get from thermometer records from the ocean, right? Okay, so what are we learning in Antarctica today? So we're just going to go to one site here that I've been working on for a couple of years. It's off the Wilkes Land margin. Was on a cruise there with Eugene and Amelia, 14 years ago, and Eugene discovered this amazing sediment body. Who was it? Oh, Matt found it. Oh my God, Amelia's husband. Is Matt here? No, okay, good. Okay, so Matt found it, and Eugene, did you interpret it? Okay, there. It doesn't, the main thing is, it wasn't me. Other really smart people. I know. Yeah, it wasn't me. Other really smart people figured it out, but we'll get to that in a moment. So this bed map, this map shows the distribution of elevations in Antarctica if you remove the ice, right? So much of Antarctica is below sea level. West Antarctica here would be this archipelago of hundreds, if not thousands, of islands with a really deep seaway. Basins here more than 2,000 meters deep. Here's the Transantarctic Mountains, South Pole around there. So, people think about West Antarctica as the soft underbelly of the Antarctic ice sheet, in part because the ice is grounded below sea level. And ocean sea level rise, all of these things tend to destabilize ice that's not really, it's not grounded above sea level. It's grounded below sea level, so it's susceptible to oceanic influences. East Antarctica, there is a huge continental area here, gambits of glacial mountains, but in this part of East Antarctica, it arguably looks a lot like West Antarctica. And so this is a frontier area right now, is trying to understand, what's going on here. Is this part of Antarctica likely to engage in rapid melting, as we think this part of Antarctica is as well? And so we visited there on Expedition 318. So Hank's brother, Dan, produced this little video, and I threw a few things on the end there. It's a big boat, it's got this giant deck, which kind of makes it move more than you really want it to. And you're going to get nailed by storms at some point going across, right? It might take 8 or 10 days there. But it's also a big boat. It's 490 feet, something like that. It's got a giant drill. These are our first icebergs. We were drilling week after week, 20 kilometers from the French base. We could smell baguettes. We could smell croissants. We thought we could smell wine. They never visited, and we did not get to go see them. The ship cost too much money. It's $200,000 a day to operate, maybe even a little more. So, it's 24/7. There's 140 people on this thing. It's a massive drilling operation with incredibly skilled drillers. These guys know what they're doing, and they do it at minus 20 degrees. So it looks like oil field drilling, and there's a lot of shared technology, but the purpose here is to collect as much of a continuous section as possible, right? So Amelia's done a lot of this kind of work over the years. Eugene's been involved in it. And, this is what life would be like on one of our cruises. So here's 10 meters of core coming in. And at this point, now finally, they keep the scientists away because we might kill ourselves. But at this point, the scientists are allowed in. There they are. And we get our first look at the core. Now the ship is our chief scientist, Carlota Escudia from Spain. The ship is equipped with this fantastic lab, and you get this kind of real-time view of the history of that part of the planet. Before you cut the core open, it's going through these the nuclear gamma system. Here it gets split, and at that point, scientists can go out and sample the material. We photograph it, we describe it, we make microscopic slides to see what it's all made out of. So you work as a team, an international team. You tend to stay connected with these people for the rest of your life. It's one of the fun things about doing life at sea, as I'm sure many of you know. So there we are, and we're going to talk about one of these cores here in just a second. So there I am at the microscope. I had this funny idea, you know, and there it is. It's kind of spooky. That was the little dinoflagellate that seems to be the evidence for water temperatures close to 20 degrees centigrade in the Eocene, when it was about the same latitude as it is today, right? So extreme warming. Okay, so let's talk about this. Here is the site. It's a deep depression here. I think this high salinity shelf water is a bit of wishful thinking on Johan's part, but we know this area by the Mertz is a major area of deep water production, high salinity shelf water. So it's a very deep depression, 1,000 meters, right next to the French base. And what Matt and Eugene sorted out when we were down there was this sediment drift deposit that's about 170 meters of Holocene mud, right? And we cored into it at the time, and this is a section of the drill core, but we saw the same thing in 2001, is these alternating layers, dark light, 170 meters of Holocene, and it pretty much all looks like that. It's a remarkable system. And it turns out, you know, at this scale, I mean, these bands, 1.6, 1.8 centimeters, you know, there's 11,000 of them in the Holocene. It all fits. It's not, you might think, oh, just count these and you'll have a perfect chronology. Well, it's not that easy, right? Because what do you do right there? It's a little bit smeared out. And that happens about every 20 or 30 centimeters. So we actually haven't been able to count bands like Richard Alley did in Greenland. But we've done a lot of work on the laminae. This is some of the work that Christina's been doing, Christina Rieselman. And we know the light laminae have a lot of open water diatoms. She's color-coded them here in green. They don't really look like that. She photoshopped it somehow. And then the dark laminae have more sea ice-associated algae. And so it makes sense. It's an annual cycle, right? Open water in the summer, sea ice production in the spring and possibly autumn, mostly in the spring, we think. In some cases, you know, you can tease apart like individual bloom events, right? This boom, Katasaurus, and that's it. Maybe it's 1 week of geohistory from 8,000 years ago. We've got a number of folks looking at that. We've put a lot of effort into age dating. It's been kind of a pain in the butt for me because I was funded to do so many dates, right? And then, okay, I start working up a model, and then the next thing I know, my colleagues in France are doing 20 more, and then in Japan say, hang on, I've got a new idea, a new technique. It's compound specific on this thing. And they just keep coming in. About every 4 months, we get a new set of dates. But we're pulling on that. This is the final chronology, and the paper is written. This is for one hole. We triple cored this site. This is the B hole, and I'll talk about the A hole in a moment. I always like, we have, you know, ODP, when they triple core, it's the A hole, the B hole, and the C hole. And we triple core because there are gaps. So these sediments are full of gas. They're organic. They generate methane like crazy. We had some explosions of cores on the catwalk. And so you lose sediment. Some of it up on the rig floor. So we triple core so we can span these gaps. So we have a bunch of dates on the other cores as well. Silicon 32 in the uppermost part, compound specific C14, a bunch of macrofossils. There's ostracods, there's clams, there's algae, macroalgae, and then bulk dates. And then this is a Bayesian kind of fitting routine. We also know how to match these cores from one to another. So here we are, this is the A hole here at the top, and then the same section, 165 meters down in the B hole, same thing at the bottom, the A hole and the B hole. And that's where I've correlated based on pattern recognition, and like, look at these things. It's kind of mind-blowing, isn't it? Look at the colors there. these reds and greens and bright yellow layers. The core is like that throughout. It's really remarkable. And we're just starting to figure out what some of those colors are, by looking. They're monospecific blooms for the most part, and there's about 4 or 5 different kinds of organisms that can monospecifically bloom and produce something like this. There's almost no bioturbation because you wouldn't observe that kind of, layer cake style laminations. So these are available as they've been available for public access for the last 2 years. This core is the most sampled ODP core at the moment. So some of the data sets that we've been working on, I would say this is one of the least interesting, but it's where we started: sediment organic carbon content 1 to 2%, delta C13, which we've been working hard to understand better for a long time. So not too much change in the Holocene. You can see these big flyers, and part of that's aliasing. Here's a sediment core with 2 centimeter thick laminations, dark, light, dark, light. And all of the ODP sampling techniques involve using these plugs or scoops that are like 1 or 2 centimeters, right? Sometimes you're sampling into a dark layer, sometimes into a light layer. And we've gone to channel sampling, but this is aliasing, and it tells us something about the extreme seasonal range. But how do you go about starting to work with something like this? I went to the ice cores of East Antarctica. Valerie Masson-Delmotte has published on the Holocene, so it's modern times here, 12,000 years ago. And this is a stack of, these are signals that are common to 5 ice cores in East Antarctica. And she came up with 2 modes of variance. This red one is the dominant mode of variance, 78% of the shared signal. It's a principal component here, but you would read this in terms of temperature, and they call it the optimum here from about 10K to 11,400 years ago, and then it got cold, and then it warmed up again in the mid-Holocene, and then here's this decline in temperature that's seen in many parts of the world in the last 4,000 to 5,000 years. So if you look at it in that sense, these are the anomalies associated with this so-called optimum time that you see in the ice cores. And we know from work in the Ross Sea, when we get C13 of organic matter that's up around -25 or so, that tends to be associated with ice edge algal blooms, that there's melting ice coming into this system. That's how we start to piece together some of that story, but we've got other indicators. So here's one, sediment delta N15. So this is total sedimentary nitrogen. And this one's pretty interesting looking, right? It has these regular oscillations. Sometimes there's a big one, sometimes it's not so big, but it's every 1,200 years you get a peak. What is that? First we thought, oh, maybe these are core breaks or something, but they're not. The core breaks are, right in the middle of some of these. So it's regular variability over and over. And on our cruise there in 2001, we did collect water samples for nitrate analysis and N15 of the nitrate. So Peter Di Fiore published this paper in 2009, and it shows concentration of nitrate here with low concentrations down here, and then nitrate N15. So 4